Okay, so the last little part that we might look at with permutations and combinations is just specifically around probabilities. And I will say, for some of these questions, this might not be the way you would go for the questions. I'm going to treat them like this and we're going to look at it under this idea, but there could be other ways that you would view these questions or other ways you would line up your probabilities, and that's absolutely perfect also. I'm going to look at them kind of under this guise anyway. But to consider the probabilities involving either arrangements or combinations here, we need to look at the total number of ways this could happen and then the number of ways that the specific case in question could happen. So for example, if I want to know the probability that 3 girls are chosen from a group of 12 people, which includes 5 girls, I would need to know the number of ways of choosing the group of 3 people. And then the specific case of choosing these 3 girls from the 5 girls. Okay, so looking at an example here, 3 cards are drawn at random from a full deck of 52 without replacement. Find the probability that the first 3 cards chosen are the Ace of Spades, 3 of Hearts, and 9 of Clubs. So for all of these questions, we seem to be choosing 3 cards. So out of 52 cards, we're choosing 3. That can happen how many ways? 22,100. So that's going to be important for us in working through all of these probabilities. The first 3 cards chosen being Ace of Spades, 3 of Hearts, and 9 of Clubs. That's one specific case. Okay, so that's one specific case. So the probability of getting this Ace of Spades, 3 of Hearts, terrible heart, and 9 of Clubs is a 1 in 22,100 chance. All 3 cards being kings. Okay, well, we need to know out of the kings, there's 4 kings, what's the number of ways I could choose 3 kings out of those 4 kings? There's 4 different ways that could happen, so there are 4 out of 22,100 different outcomes where I could choose all kings, which is 1 over 5525. 2 are black and the last one is a diamond. Okay, we're looking at the specific case here. So we're just going to look how many different ways out of a set of cards could I choose 2 black cards and 1 diamond. So out of all of the black cards, I want to choose 2, and out of the diamonds, I want to choose 1. So 26, let me just set this up, 26 choose 2, and 13 choose 1 is 4,225. So the probability then of this happening is that out of the total outcomes, which is 22,100. And again, we can see where that would 13 out of 68 here. Okay, and lastly, all 3 cards are of the same suit. Okay, the different ways that could happen would be that they're all hearts, or all diamonds, or you can guess for yourself, all clubs, or all spades. So those are my 4 kind of different setups here that I need to consider. Okay, we'll find the probability for each of these. So out of the hearts, out of the 13 hearts, I want to choose 3. So how many ways could I choose 3 hearts? 286 ways. That's going to be the same for all of my individual probabilities here. So it's 286 over 22100. We're adding them together or simply multiplying them by 4. 286 over 22100 times 4, which will give me 22 out of 425. Okay, so nice example. We'll continue into some of these exam questions here. And as I say, some of these, trying to apply the probability rules to them can seem a little tricky, but you need to focus just on that idea of looking at the overall scenario. So how many ways can this happen? And then the individual situation here, how many ways can this individual choice be made? So how many ways can a jury of 12 people be selected from a panel of 8 men and 8 women? So out of 12 people, we're choosing, or sorry, out of 16 people, I am choosing 12 people. So 16 choose 12 is 1820. Find the probability that one such jury selected at random will contain more men than women. So that could be, if it's a jury of 12 people, that could be 7 women and 5 men, or it could be 8 women and 4 men. And that's the maximum we can do. So let's find out how many ways can I choose 7 women and 5 men. Well, out of the 8 women, choose 7, and then out of the 8 men, choose 5. So that's going to be 8, choose 7, 8, choose 5, 448 ways. This is an OR, so that's suggesting we add these probabilities here in this case. Okay, this is now 8, choose 8, and then 8, choose 4, which is 70. So there are 518 total ways that this situation could happen. In terms of a probability then, that is 518 out of 1820. And again, we can see if that simplifies down. I don't know whether it does, but it does. 37 over 130. Okay, so it does reduce down for us. Let's look at another example. A class consists of 12 boys and 8 girls. 2 students are selected at random. What is the probability the 2 selected will be a boy and a girl in any order? Well, we'll look at probability here. So the probability, we need to get a total number of ways that this arrangement could be made. So out of 20 people, choosing 2 people, how many ways are there of doing that? 190. Then we look at the specific case. So out of the 12 boys, I want to choose 1. And out of the 8 girls, I want to choose 1. That's going to give me, what, 96. 98, choose 1. 96 here. So the probability then is 96 out of 190, which is what? 48 out of 95. So the probability of 1 boy and 1 girl, 48 out of 95. 4 students are selected one at a time at random from the class. What is the probability that the first 3 students selected will be boys and the 4th will be a girl? So let's just list out what we want here. We want boy, 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 girl. If I was to ask myself what word would I be using there, it would be the word and. The probability of getting a boy out of the class here is 12 out of 20. So we're basically saying 12 out of 20 times 12 out of 20 times 12 out of 20 times 8 out of, 12 out of 20. And then the probabilities, of course, are going to change. 11 of 19, 10 out of 18, 8 out of 17. Okay, the probability on the bottom changing because we're not replacing these people either. We're selecting them from the group. Obviously, as I select boys, the probability of the boys goes down. We would say that each of these is not independent because choosing a boy the first time is having a knock-on effect on the choice coming down the line. 8 out of 17, so 88 out of 969. Okay, on to the next one. Okay, we're getting through these rightly. This question here, okay, the school caretaker has a box of 23 room keys. 12 are for general classrooms, 6 for science labs, 5 for offices, 4 are chosen at random. What's the probability the 4th key drawn is the first office key drawn? What we're kind of missing in this is whether there's replacement or not. And obviously that's going to have a little bit of an impact on the question here, but let's just try and lay it out at normal. 4 keys are drawn from the 23 keys, so out of the 23 keys there are 4. If I was to lay it out using kind of my combination idea here, just to look at that, 23 choose 4, that's 8,855. We may not even need to use combinations to help us answer this one here at all. The 4th key drawn being the first office key means I want not the office, not the office, not the office, and then the office here. I'm going to say that if I'm drawing these out, that I wouldn't be replacing them realistically. I don't know why I would replace them and put them back in again. So not getting an office key the first time, only 5 are for offices, which means 18 are not for offices. So if my first key is not an office key, the chance of my next key not being an office key is 17 out of 22. Then 16 out of 21, and the last one is going to be an office key, and there's a 5 in 20 chance that it is an office key, and that's 0.1152 as a probability there. So that's without replacement. Okay, I'm fairly sure if I remember right, the marking scheme for that one considered without and with replacement because the question doesn't really specify. Looking at part 2, all the keys are returned to the box. 3 are drawn at random from the box, one after the other, without replacement. So maybe the fact that it mentions replacement here maybe suggests that there is replacement on the first one. What is the probability? 1 is for classroom, 1 for science, and 1 for office. Okay, I suppose what's interesting here is there's no mention of kind of us looking after each one. Obviously, if we're doing the previous question, we had to check after each key to see if it was an office key. But here we're just taking 3 out and then kind of looking at them. So we want to choose 1 for general classroom. So out of the 12 keys for general classrooms, we want to choose 1. Out of the 6 keys for science labs, I want to choose 1. And out of the 5 keys for offices, I want to choose 1. So let's try that. 12, choose 1. 6, choose 1. And 5, choose 1. 360. So there's 360 different ways that I could choose 1 of each key. If I go for probability, then there's 360 different ways of choosing 1 of each key out of the 8,000. Or sorry, I'm only drawing 3 keys, excuse me. So out of the 23 keys, I want to draw 3. So let's do that. 23, choose 3, which is 1771. So that gives me 360 over 1771, which can't reduce down. So we leave as is. Okay, or they said, sorry, to 4 decimal places. I knew I typed it in for a reason. So 0.2033. Okay, so again, low enough. Well, 20%, not that low, I suppose. So I think this is our last little question here for this section. In how many different ways can 8 people be seated in a row? This is an arrangement, so 8 factorial different ways of arranging people in a row. And that's 40,320, so quite a few as it happens. 3 girls and 5 boys sit in a row arranged at random. Find the probability that the 3 girls are seated together. Okay, so since the 3 girls are seated together, that means we are only arranging 6 objects. Okay, so we have the block of the girls, and then we have the other objects of the 5 boys. Okay, we also know that this block with the girls can be arranged in 3 factorial different ways. So we have the 3 factorial different ways of arranging the girls and the 6 factorial different ways of arranging everybody here. Okay, so that's 3 factorial times 6 factorial, which gives me 4,300 different ways of arranging them. So the probability then that the girls are together is in 4,320 out of the 40,320 possible outcomes. And we'll see, does that reduce down for ourselves here? 4320, 3 out of 28 here. Okay, last section here, last question. 3 girls and n boys, so we're not told how many now, sit in a row arranged at random. We're going to apply it in the same way if we can. Find the probability that if the probability the 3 girls are seated together is 1 out of 35, find the value of n. Okay, so let's see the total value here. So out of 3 plus n, we're arranging these different people here. So the total arrangements is 3 plus n factorial. Okay, and excuse me, I'm trying to jump straight into this question. I need to read it again. 3 girls and n boys sit in a row. The 3 girls are going to be seated together, which means we are arranging the block of the girls and the n boys, which means we're arranging n plus 1 objects. So the total number of arrangements then is n plus 1 factorial. Okay, the 3 girls being seated together are the number of ways of arranging these particular. Okay, so the number of ways, I suppose, of looking at this particular arrangement here. Okay, so n plus 1 factorial, and also consider that the girls can be arranged in any order with the 3 factorial. So 3 factorial, of course, 6. So 6 times n plus 1 factorial. I shouldn't say, actually, that's not the total, that's the specific case. the total arrangements, okay, the total way of arranging all of these people, girls and boys, is n plus 3 factorial. Okay, so this specific case where I want the girls to be together, there is n plus 1 ways of arranging this block of girls and all of the n boys. And we also consider the 3 factorial different ways of arranging the girls within their little block. So that's 6 times n plus 1 factorial. There's a total of n plus 3 factorial arrangements that can be done. So setting all of this up now, 6 times n plus 1 factorial over n plus 3 factorial should be equal to 1 over 35. So we have a little bit of work to do on this one then, to do some rearranging and some kind of simplification to some extent on this one. Okay, so let me take this over to the side here. So 6 times n plus 1 factorial. I'm going to reduce or write out my n plus 3 factorial here. So n plus 3, n plus 2, n plus 1 factorial, still equal to 1 over 35. The fact that I have the n plus 1 factorial on the top and the bottom means I can reduce it to 6 times n plus 3, n plus 2 equals 1 over 35. Let's do some multiplication here. 6 by 35 to 10, n squared plus 5n plus 6, n squared plus 5n minus, what would that be, 204 equals 0. Okay, we want to solve our quadratic here. We'll get an answer of n equals minus 17 and n equals 12. Since n is a number of boys, we can't have a negative number of boys, so we'll go with n equals 12 there. Okay, so a little bit of work, and you can even see there kind of me working my way through it nearly to some extent there as well, but just identifying there, you're always looking for the total arrangement, so that's irrespective of any restrictions given there. So that's kind of, I was getting caught up on that restriction on the girls. The total arrangements is irrespective of that. It's just how many people are there and how many ways could I arrange them, and then looking at the arrange or the restriction there gives us more of the specific arrangement for this question, and then using that then in working with the factorial notation again as before. But I suppose overall, working with these probabilities, it really is following those steps we identified at the start, looking at the total ways this could happen and the specific number of ways that this specific case could happen. And that's really going to help you then in just kind of identifying the probabilities and in not getting kind of caught up in thinking about it all together.